right, this video is on chapter 13, control of microbial growth. So microbes are everywhere. And so this video is just showing you that, or this picture is just showing you on different parts, the colony forming units per 6 by 6 centimeter area. The door latch was by far the most contaminated, and the center console. But just kind of giving you an idea, like it doesn't matter like where it is, you're going to find a whole bunch of bacteria. And so our goal with this is, how are we going to mitigate that and reduce those numbers in order to keep things clean? So it's going to depend on what your goal is overall, as far as what methods you take. So this chapter is going to go through how to clean surfaces. We'll talk about antibiotics in the next lecture. Okay, so controlling microbial growth, we're going to compare disinfectants, antiseptics, and sterilants, and then talk about the principles for controlling microbes through sterilization and disinfection, and then differentiate between the different biosafety levels. So this is a picture of two lab workers in suits that completely cover them. So this would be like a biosafety level 4 type situation, where you've got forced air in and out, and it's a shower in, shower out. They are trying to lower the number of bacteria or viruses that they're carrying out of this contaminated area. So this is the BSL levels. BSL level 1 is basically what we're working with in the lab. So you have BSL1, BSL2. We work with both of those levels in our lab. So BSL1, microbes are not known to cause disease in healthy hosts and pose minimal risks to workers and the environment. So this is those non-pathogenic strains of E. coli. So when we're working with E. coli in the lab, that's what that is. BSL2 levels, these guys are typically indigenous and are associated with disease of varying severity depending on the host, and they pose moderate risk to workers. So Staph aureus is everywhere, but when it gets to a spot where it's not supposed to be, it could cause disease, or if it gets in where it's not, or in a person that is maybe not healthy, it will cause even worse disease. BSL3, microbes are indigenous or exotic and cause serious or potentially lethal diseases through respiratory transmission. That's the key there. So this is like Mycobacterium tuberculosis. So this is very controlled. There's going to be negative pressure. It's going to be a shower in, shower out scenario, most likely. Some of them have what we call a PAPR, which is kind of what you saw in that video, that picture right before, but it's a purified air apparatus that just goes over the head. It doesn't cover the whole body. BSL4, there are very few labs. There's only 2 in the United States. One's at Kansas State, and the other is in Atlanta, Georgia. So these are dangerous and exotic, posing high risk of aerosol transmission, which are frequently fatal without treatment or vaccines. There are very few labs. So this is like Ebola and Marburg. So this is showing the biological safety cabinets in the different classes. The one that we use in our lab is a class 1 cabinet. We don't have any class 3 cabinets because that's a BSL4, because you have to have a suit. It protects the, actually that one might be a class 2 because it does protect the product as well. So that one is probably a class 2, to be honest. It protects the personnel, the environment, and the product. I would screenshot this. This is a great breakdown of these different words. So disinfection reduces or destroys microbial load of an inanimate object through application of heat or antimicrobial chemicals. So this is not used for people. Okay, you don't disinfect a person. Okay, that is antisepsis or degerming. Okay, so these first 3 are on fomites, so like sterilizing your bench tops and those kind of things. So cleaning surfaces like your benches, clinical surfaces, and bathrooms, you use bleach, phenols, and glutaraldehyde. You don't ever use bleach on yourself. Sanitization reduces microbial load of an inanimate object to a safe public health level through application of heat or antimicrobial chemicals. So this is like your dishwasher for the cleaning of eating utensils, cleaning public restrooms. So detergents containing phosphates, um, or your quaternary ammonia product. Then there's sterilization. So this eliminates all vegetative cells, all endospores, and all viruses from an inanimate object. This is for surgical equipment and needles used for injection. Pure pressurized steam, like an autoclave, which I'll show you guys that in our lab. Chemicals and radiation. So those all can be used on an inanimate object. The other two are used on living surfaces because we can't use those harsh chemicals in those ways. So antisepsis reduces microbial load on the skin through the application of some type of chemical, cleaning skin that's broken due to injury, cleaning skin before surgery. So boric acid, isopropyl alcohol, hydrogen peroxide, or iodine or betadine. Degerming, so reduces microbial load on skin or tissue through gentle to firm scrubbing using a mild chemical. So this is going to be hand washing, and that's like soap or alcohol swabs, or like your hand sanitizer. So some words, some suffixes you need to know. Side means to kill, so bacterial side, virus side, fungicides. Those all kill bacteria, viruses, and fungi. Static just means that it inhibits the growth. So bacteriostatic, fungistatic inhibits growth. There's the microbial growth curve will progress and effectiveness of the protocol to kill the agent. So we can look and see how well this is going to kill the bacteria based on that curve. The decimal reduction rate, or the D value, is the amount of time it takes for a specific protocol to produce 1 order of magnitude decrease in the number of organisms, or death of 90% of the population of the bacteria, not of people. So this is showing the death curve and the D value. Okay, so this is the microbial death is logarithmic and easily observed using this semi-log plot instead of an arithmetic one. The decimal reduction rate is the time it takes to kill 90% of the population, or a 1 log decrease in the population when exposed to a specific protocol. So this is showing the number of bacterial cells over time. Love this. I would screenshot this as well. This is showing the three categories we're going to talk about: physical agents, chemical agents, and mechanical agents. So for physical, we've got heat and radiation. Heat can either be dry or moist. Dry would be incineration or the dry oven that achieves sterilization. Moist, under pressure, gets you sterilization, which is your autoclave. Boiling water, hot water, pasteurization just gets you to disinfection. Radiation, you've got two different achievement levels here. You've got ionizing, which is going to get to sterilizing. Those are your X-rays, cathodes, and gamma rays. Ionizing, which is UV, we did this in lab, that's just going to be a disinfection. Chemical agents, gases or liquids. So gases, you can achieve either sterilization or disinfection depending on the concentration. Liquids, on animate objects, you get antisepsis. On inanimate objects, you can achieve sterilization or disinfection depending on the concentration. Mechanical removal, filtration in air is decontamination or sanitization, same word. Liquids would be sterilization. Relative resistance of different microbial types. So the most resistant is prions, which is those proteins. They have that I talked to you about. So they have actually tried to incinerate these guys. They've buried them, they've autoclaved them, and they're still functional. It's insane. But next would be your bacterial endospores, mycobacterium because of their waxy coat, staph and pseudomonas, protozoal cysts, protozoal trophozoites. Gram-negative bacteria are less resistant than the than your mycobacteriums. Then you have fungal and fungi and fungal spores. Non-enveloped viruses. Most gram-positives are pretty sensitive to things, and then you've got your enveloped viruses. So bacterial Endospores are considered the most resistant microbial entities. Destruction of endospores is the goal of sterilization. Any process that will kill endospores will kill everything else except for prions, of course. And then other methods of control, disinfection and antisepsis, act on microbes that are less hardy than those endospores. I think this is so interesting. So this is comparing the resistance of bacterial endospores and vegetative cells to control agents. So the first column is your endospores, and the second column is your vegetative spores or forms. So for heat, it takes up to 120 degrees Celsius to kill an endospore, but only 80 degrees for a vegetative. So that's a natural growing cell. So that's only 1.5 times more. Radiation or X-rays takes 4 times more, so 4,000 grays versus 1,000 grays. Sterilizing gas 1.7 times, so that'd be 1,200 milligrams per liter versus 700 milligrams per liter of the ethylene oxide. Sporicidal liquid 2%, so this takes 3 hours of contact or 10 minutes, so that's 18 times more. Interesting. Okay, so let's talk about physical control methods. So we're going to talk about all of these. So, oops, wrong direction. Thermal death point is the lowest temperature at which all microbes are killed in a 10-minute exposure. And thermal death time is the length of time needed to kill all microbes in a sample at a given temperature. And we're going to talk about dry versus moist heat. So heat is an agent of microbial control. So we have moist heat, like hot water, boiling water, and steam. Temperatures range between 60 to 135 degrees Celsius. Temperature of steam can be regulated by adjusting the pressure, and that's where the autoclave comes in. So I'm going to show you guys the autoclave and how that works. It operates at lower temperatures and shorter exposure times than dry heat. So it's a lot more effective in a shorter amount of time. Most microbicidal effects is coagulation and denaturation of proteins to quickly and permanently halt microbial metabolism. So we want to denature and make those turn into goo. Dry heat, air with a low moisture content that has been heated by a flame or electric heating coil. You guys do this all the time when you're flaming your loops. Temperatures range from 160 degrees Celsius to several thousand degrees Celsius. Dehydrates the cell. Lack of water increases the stability of some protein configurations, necessitating higher temperatures. At high temperatures, dry heat oxidizes cells, burning them to ashes. So this is interesting too. So this is the comparison of times and temperatures to achieve sterilization with both moist and dry heat. So moist heat at 121 degrees, it only takes 15 minutes. But at 121 degrees Celsius for dry heat, it takes 600 minutes. That's a lot longer. 125 degrees, 10 minutes, 134 degrees, 3 minutes. Where you can see that the dry heat takes just a lot longer to sterilize. So this is showing your flame and your ceramic incinerators there. This is an autoclave, and I'll show you guys this in class. There's white strips that are used. That's called autoclave tape. It will turn dark once the autoclave has reached a specific temperature and pressure, and that's supposed to tell you that these tubes are sterile. But the caveat here is that anaerobic situations can also change this strip, so you got to be careful there. Pasteurization, there are 2 different kinds. There's HTST, which is milk that's heated to 72 degrees for 15 seconds and then bottled and refrigerated. So it's a flash heat. Okay. Or there's UHT, which is heated a lot higher for only 2 seconds, then sealed, and it's good for up to 90 days. So this is like that stuff that's at room temperature. That always freaks me out when I see like the milk that's on the counter. Freaks me out so bad. But I guess it's okay. Milk-borne organisms killed by pasteurization is Campylobacter jejuni, Coxiella Burtonii, Listeria monocytogenes, E. coli 0157H7, that's the nasty one, Mycobacterium tuberculosis, Mycobacterium paratuberculosis, Salmonella, and Yersinia, and Enterocolitica. So all of these methods will kill those. Effects of cold. So cold treatment does not do anything to kill microbes. It just slows them down. Some of them can be killed if they're really weak, but most of them are not affected by cooling, or long-term refrigeration, or even deep freezing, because that's how we actually store them, is by freezing them. So this is, some of them, maybe wimpy ones, can be killed, but not very many. Desiccation is dehydration of vegetative cells directly exposed to normal room air. Some delicate pathogens can be killed by a desiccation, but most of them are preserved this way. We lyophilize them, which we'll talk about that in a minute, but we dry them out and then put them in a powder, and then we can reconstitute them later. Desiccation can preserve foods because it reduces the amount of water available to support microbial growth. So that's why you dry meat out and dry fruits out, and that will really stop the microbial growth as well. Lyophilization is a combination of freezing and drying, common method of preserving microbes and other cells in a viable state. Pure cultures are frozen instantaneously and exposed to a vacuum that removes the water. And then it just basically has them in this state of no growth, and then they can be reconstituted with water later and warmed up and brought back to life. Cultures, so this is storing them at the ultra low -70 degrees Celsius. This is showing the US Navy's stockpiles. And this is liquid nitrogen, is also another way of storing those cultures. Osmotic pressure, we talked about this when we did the osmosis lab. Adding large amounts of salt or sugar to foods creates a hypertonic environment, causes plasmolysis in the bacteria, makes it impossible for a bacteria to multiply. Cured meats are treated with high salt concentrations so they can be kept for long periods without refrigeration. High sugar in jams and jelly has the same effect. Honey, too, is that way. So Clostridium botulinum is in botulism. So a pressure canner can reduce or decrease these endospores because it gets to a high enough pressure that kills those. But you want to be really careful when you're doing home canning, and also make sure you don't eat cans that are distended from the store. You never eat a dented can or a swollen can. So the addition of solutes creates that hypertonic, draws the water out of cells. So here we've got raisins and jerky, some dried fish, and then jams and jellies also are a good way of preserving. Radiation as a microbial control agent. So energy emitted from atomic activities and dispersed at high velocity through matter and space. So this is showing the wavelengths of light. So we have visible light, which was what we see, which is not harmful. So you have infrared, microwaves, radio waves are all longer wavelengths. It's when you get to these shorter wavelengths that you have the issues. UV, X-rays, gamma rays. So the shorter the wavelength, the more damaging it is. Irradiation is the bombardment of microbes with radiation. So if it's ionizing radiation, it can go through a barrier and break up the DNA. Non-ionizing does not penetrate through a barrier. That's why we had to take, for UV, that's why we had to take the lid off of those plates. And then what it does is it makes DNA without the barrier. It makes the DNA form these thymine dimers. Cold sterilization is ionizing radiation used to sterilize materials, used for materials that are sensitive to heat or chemicals. So irradiating food or cold sterilizing food is what is used a lot of the time. So if you did heat with meat, it would cook it, and that's not good. But there will be a little marking if it's been irradiated. Of course, there's no radiation left over, so it is safe consumption. Ionizing radiation, which is your gamma rays and X-rays, ejects electrons out of an orbital from an atom, causing ions to form, causes mutations in the DNA and damages proteins. So those are the shorter wavelength, higher effective sterilization methods. Non-ionizing UV rays excites the atoms, raising them to higher energy state, leads to the formation of abnormal bonds in the DNA. Thymine dimers. That's a test question. UV ranges from 100 to 400 nanometers. Most lethal between 240 and 280 with a peak at 260. A germicidal lamp generates 254 nanometers. Not as penetrating as ionizing radiation, passes readily through air and slightly through liquids and poorly through solids. The object to be disinfected must be directly exposed to it for the full effect. Initially absorbed by the DNA, they form pyrimidine dimers or thymine dimers normally, but they can also be affected by the cytosine as well, interfere with abnormal DNA replication and transcription, and lead to growth, inhibition, and death. So it causes these thymine dimers between the T's. UV causes these dimers and lead to lethal mutations. Germicidal lamps emit the UV light to sterilize the equipment. We saw that in the cabinet when we did that lab. So foods can be exposed to gamma radiation on a conveyor belt, and that's what this looks like. This is the irradiation symbol. And that's makes the food safe. HEPA filters are going to remove microbes, endospores, and viruses depending on the size of the filter. So this is showing what happens. You've got these randomly arranged fibers. So you have interception, impaction, and diffusion. So it's going to impact it. It's going to, as they are used, they actually get more efficient because they clog up more and they can stop more stuff. Membrane filters. So this is for things that cannot be autoclaved. Maybe they have something in them that will be denatured, especially antibiotics and other blood products that you add to medias. So what you do is you put the liquid in the top, you apply the suction or the vacuum, and it pulls it through a membrane. So depending on the pore size of the membrane, you can really filter out a lot. This is also not the most effective way, this syringe, but it'll work as well. You just put it out on the end and then shoot it into wherever you're gonna put it. So this is showing filtration. So this is an effective method for removing microbes from air and liquid. Liquid is strained through a filter with openings large enough for the liquid to pass through, but too small for the microbes to pass through. Most filters are perforated by precise uniform pores. So coarse would be 8 microns, and then ultrafine would be 0.02 microns. Allows selection of minimal particle sizes to be trapped. Even smaller pore diameters permit true sterilization by removing viruses and even some proteins. You got to be careful what you're trying to get out of there. Used in liquids that cannot withstand heat, like I said. It's an alternative method for decontaminated milk and beer. Important step in water purification, and it's efficient means of removing airborne contaminants. So I would screenshot this, take a look at this. This goes through all of them. Some of them we didn't talk about, like pressure. But yeah, this goes through all of them. There's more. Sonication we didn't talk about. That's the exposure to ultrasonic waves that'll lyse the cells. That's how they clean jewelry and stuff like that. Okay, so chemical control methods. Now, I'm not going to make you guys know all of the chemicals, just the categories, basically. And then there's going to be some that are important, okay? Factors that influence the rate at which microbes are killed by antimicrobial agents. is going to be the time in minutes. So how long are they exposed? What this is saying is the longer that it's exposed, the more it's going to get sterilized. And so if you don't, there's going to be a time on most of these chemicals that say it has to have contact. It's called a contact time. Um, for a certain amount of time in order for it to be effective. The number of cells, higher load is going to take longer to sterilize than a lower load. And then is it a spore or is it a vegetative cell? And then the type of agent. Is it microbicidal or is it microbistatic? Those are basically what that says. So, how these agents work, there are different targets for both the physical and chemical agents. So, the cell wall, the cell or the cytoplasmic membrane, cellular processes like DNA and RNA, and then proteins. So, effects of agents on the cell wall, they damage the cell wall by blocking cell wall synthesis, digest the cell wall, or break down the surface of the cell wall. A cell is damaged. A cell with a damaged cell wall is fragile and becomes lysed easily. So you're looking at detergents and alcohols are what are going to break up that cell wall. The cell membrane, disruption of the selective permeability, loss of vital molecules, and allows entry of those chemicals. Surfactants, these are polar molecules with hydrophilic and hydrophobic regions that basically just disrupt the membrane. Remember, we talked about how it's amphipathic. Well, these guys are polar and they're going to go in there and they're going to mess it all up. So they bind to the lipids and penetrate the internal hydrophobic regions and make leaky spots that allow for the chemicals to seep in and cause the ions to leak out. And that's what this looks like. So it inserts and then it just disrupts those membranes and then doesn't work anymore. Agents that affect protein and nucleic acid synthesis. So you have microbial cells depend on an orderly and continuous supply of proteins. So if a substance will inhibit ribosomes, then you won't have protein synthesis. If you have some that impede the transcription or translation of DNA, then you won't have proteins either. Protein states affect the function. So we kind of talked about this when we talked about protein folding, but you have the native state, which is that three-dimensional or quaternary conformation. And when it's denatured, it's been disrupted and rendered non-functional. So you break those bonds that maintain that secondary and tertiary structure. Maybe it's the covalent bonds or the hydrogen bonds or the disulfide bridges or something. It's going to disrupt that. It's going to make them flat and they're not going to be functional. Denaturing of protein. So moist heat is an irreversible like the irreversible solidification of an egg white. You can't get that back. Strong solvents like alcohols and acids and phenolics will denature proteins. Other effects, metallic ions bind to the active site, preventing them from interacting with their substrates. So this is showing complete denaturation. So you have your native state where the substrates can bind. And then if it's denatured, it's going to be flattened. If it tries to reshape, it might come back the wrong way. Or you might have these agents, that will block those active sites. Chemical agents in microbial growth. So they could be solid, liquid, or gas. For convenience, solid and gaseous antimicrobial chemicals are dissolved in water, alcohol, or a mixture of the two. If it's an aqueous solution, the water is the solvent. If it's a tincture, that means that it's dissolved in pure alcohol or an alcohol water mixture. So you might hear those words. If it's a aqueous, that's water. Tincture has alcohol. So desirable qualities of a germicide. So rapid action at a low concentration because we don't want to cause any other issues with the chemicals. Solubility in water or alcohol and long-term stability. Broad spectrum microbicidal action without toxicity to humans and animal tissues. Penetration of inanimate surfaces to sustain a cumulative or persistent action. Resistance to becoming inactivated by organic matter. That's huge because a lot of the times organic matter in this case is normally like feces or food If the agent is inactivated by that, then that's a problem. Non-corrosive or non-staining properties, sanitizing and deodorizing properties, and affordability and readily available. High-level germicides will kill endospores, sterilants if used properly, used on critical items that are not heat sterilizable, so like catheters, heart, lung equipment, and implants. Intermediate germicides kill fungal but not bacterial spores, resistant pathogens such as tubercle bacilli or mycobacterium, and viruses, used to disinfect semi-critical items like respiratory equipment and thermometers. Then we have low level, which eliminate only the vegetative bacteria, vegetative fungal cells, and some viruses, used to clean non-critical materials like electrodes, straps, and furniture that touches the skin but not the mucous membranes. Factors affecting microbicidal activity of chemicals. So the nature of the microbe, the nature of the material being treated, the degree of contamination that you want to achieve, time of exposure, and strength and chemical action of the germicide. Cellular targets of germicides. So most of them, like we said, act on proteins, nucleic acids, cell walls, and cell membranes. Saying this again, so it's probably pretty important, right? So you don't have to know all of these. Just know that there are different categories. I'll let you know which ones are the most important, but I have to talk about them. So a halogen are your fluorine, bromine, chlorine, and iodine. They are both microbicidal and sporicidal, active in ingredients in about a third of all antimicrobial chemicals. Chlorine can be either liquid or gaseous. You can also have hypochlorites or chloramines. These kill bacteria, endospores, fungi, viruses. Less effective if exposed to light, or an alkaline pH and excess organic matter. So again, that's what's gonna knock that one out. Hypochlorites are broadly used in industry and health. Household bleach is a weak solution of sodium hypochlorite. Chloramines are used as alternatives to pure chlorine in water treatment. Iodine and its compounds, so you have a free iodine and iodophores, which are all classes of organisms, can be killed by iodine if proper concentrations and exposure times are used, not adversely affected by organic matter and pH. The problem with those is that it stains. Aqueous iodine is a topical antiseptic, treatment for burned and infected skin. Iodine tinctures are used in skin antisepsis. Iodine tablets are used in disinfecting water. And iodophores are complexes of iodine and alcohol and have replaced free iodine solutions in medical antisepsis. Phenols and its derivatives. This is the first major antimicrobial chemical used. It's toxic and irritating side effects. Phenolics destroy vegetative bacteria, fungi, and most viruses, able to act in the presence of organic matter, has a detergent action. It is too toxic to be used on skin as an antisepsis. Cresols are a phenolic derivative combined with soap. Bisphenols are aerosol sprays and cleansing soaps. Triclosan is a disinfectant and antiseptic chemical added to many products. Hexidine is used in hand scrubbing, surgical prep, and other medical uses, but it's going to be very dilute, very, very dilute. Alcohol. So this one's important. So remember this one. Only ethyl and isopropyl alcohol are appropriate for microbial control. Greater efficacy at 70% or higher. Destroys vegetative microbial forms, but not endospores. More effective against enveloped viruses than non-enveloped viruses. Ethyl alcohol between 70 to 95% is used for skin degerming and disinfection of some types of medical equipment. Evaporation rate limits the effectiveness. So if you've ever put this out there, it'll evaporate pretty quickly. Isopropyl alcohol, more microbicidal and less expensive than ethanol. Evaporation rates are also an issue, and vapors can actually adversely affect the nervous system, so you got to be careful with those. Hydrogen peroxide is germicidal due to the toxic reactive oxygen species in there. They've got, or agents, I guess I should say. It's bactericidal, fungicidal, virucidal, and sporicidal at very high concentrations. It's an antiseptic, skin and wound cleansing, bedsore care, and mouthwashes. Can also be a disinfectant for soft contacts, surgical implants, plastic equipment, utensils, bedding, room interiors. Sterilization of delicate reusable instruments. It can be vaporized, so it can be used to disinfect small spaces and also large enclosed spaces. Ozone or O3 has similar effects of H2O2 or hydrogen peroxide. Surfactants, like I said, they have limited microbicidal power due to the amphipathic nature of the molecule. They disrupt the selective permeability. They have varied effects, activity reduced by the presence of organic matter. Quaternary ammonias or quats for ophthalmic solutions and cosmetics, soaps, disinfectants mixed with cleaning agents to sanitize a variety of objects. Can also be used in preservatives, weak microbicides. Pseudomonas grows abundantly in soap dishes, so it really doesn't do a whole lot there. Mainly used for mechanical removal of microbes and more germicidal when combined with chlorhexidine and iodine. So this is showing the non-germicidal soap versus the germicidal soap and the millions of bacteria over days. So having the germicidal soap is going to reduce those quicker. Heavy metals, they are oligodynamic, which means they're toxic in minute quantities. So this is silver and gold foil, which will inhibit the growth of bacteria. Only mercury and silver compounds have significance as germicides. Drawbacks here is toxic to humans if ingested, can cause allergic reactions, neutralized by biological waste, and microbes can develop resistance pretty quickly. Applications, weak or organic mercury tinctures are effective antisepsis and infection preventatives. Preservatives in cosmetics and ophthalmic solutions. Silver compounds, so silver nitrate is a topical germicide. Silver sulfadiazine is used in burns. Pure silver is incorporated into catheters. Colloidal silver is a mild germicide, and silver ions can be incorporated into hard surfaces and textiles. There's a brand of wash rags that has silver in it. I can't remember what they're called. They used to like sell them all over the place. I'll think about it later, but they have silver in them and they say that they are germicidal. So aldehydes, you've got glutaraldehyde, which is rapid, broad spectrum, accepted as a sterilant, retains potency in the presence of organic matter, so that's a good thing. Formaldehyde, formalin is the aqueous solution. That's what we put all of the organs in that are in those cups. It has intermediate to high level disinfectant properties, but it's extremely toxic. Orthyl phentaldehyde or OPA is similar to glutaraldehyde. It's less irritating, but it does not destroy endospores. Applications, glutaraldehyde sterilizes materials damaged by heat. Formalin disinfects surgical equipment, is used in aquaculture, and it's the active ingredient in embalming fluid. So that's what's going to keep the body from decaying over time after death. Gaseous sterilants, ethylene oxide. Chemiclave is a chemical sterilization. It's explosive and a carcinogen, so you do not want to breathe it in or get it in your eyes or mucous membranes. It's very, very, very bad. Chlorine dioxide is used for treatment of drinking water, wastewater, Food processing equipment and medical waste used to disinfect the Senate offices after the anthrax attacks in 2001. Acids and alkalis, aqueous ammonium oxide, you have detergents, cleansers, and deodorizers. Organic acids are used in food preservation like acetic acid, propionic acid, lactic acid, benzoic acid, and sorbic acid. This is a list of your normal ingredients to commercial products. So Lysol is an acid, Clorox is a quat, Dial is a surfactant, Lysol is a quat and an alcohol. Wet ones are a detergent or a quat. Noxema triple cream is an alcohol and an acid. Scope is an alcohol. Purell, alcohol. Colgate has phenolic compounds. It did have triclosan, which has been allowed, except they did ban the triclosan. Okay, so this is an exception to the triclosan ban. So they did add a little bit of it to Colgate. Okay, that's it for physical and chemical control methods.